I am Hyeong-Yeon of Korea Atomic Energy Research Institute. The title of my presentation again is, enhancing the integrated piping system subjected to long-term operation at high temperature in the crib range. The outline of my talk is first introduction, next integrity issues of high temperature piping, next technical issues of conventional power piping code of ASMP 31.1 and the alternative rules. Next, enhancing integrated hot with steam piping in thermal power plant, elevated temperature evaluation platform called HITEP in-house program, and this application to a piping, and I will conclude my talk. Let me start my talk with the cracks detected repeatedly at the welded joint of a hot with steam piping. This is the actually crack map of a thermal power plant in Korea. And the cracks, as many as 22 cracks were detected. And they have been detected at the welded joints of FM steel, that is P91 and the P92. And they are known as a type of cracking at the fine grain heat affected zone. And the cracks, the important thing is the crack occurred after a certain period of time, which means effects of a creep was significant. And so those crack issues needed to be addressed associated with the design of a component or a piping made of P91 and the P92 for not only supercritical thermal power plant, but also for the generation 4 nuclear reactor systems. Let me talk about the integrity issues. There are a number of causes of defects and the cracks, such as design problem, fabrication problem, installation problem, material operation control, and so on. Then how can integrity be enhanced? There may be many ways, such as development new materials and their applications, although it may be quite expensive. And other things such as application of improved ND maintenance method and the real-time monitoring systems and so on. My talk today will be focused on the low-cost, high reliability method associated with addressing those crack problems in a power piping subject to long-term operation in the crib range, mainly focusing on more analytical rather than experimental work. The first one is application of nuclear design rules rather than conventional rules to thermal power plants. That means a piping design rules, conventional piping design rules of ASMP 31.1. On top of that design rules, we can apply nuclear design rules of RCC MRX, which will be explained in later screen, and lowering overall stress levels of a piping system through optimized piping layout and the elimination of redundant pipe supports, if any. Let me talk about the technical issues of P31.1. It is actually design rules for power piping, which is simple to apply, but there is a concern on conservatism in case of a long-term operation in the crib range. For short-term operation, there's no problem. But in long-term operation, since crib effects are not taken into account explicitly, it was shown from many previous research of our team that it could overestimate, and there is a non-conservatism in case of long-term operation. Actually, P31.1 is originally developed for low temperature piping design, but it has been extended to high temperature design of the high temperature in the crib range. So as you can see here, the design rules that should be satisfied is a stress limits and the fatigue limits. But in actual general high temperature design and evaluation, the 4 limits should be checked. not only for stress limits and the fatigue limits, strain and the creep fatigue limits should be satisfied. That is the technical issue. But in case of alternative design rules like a US ASME code or HB and the French RCC MRX code, or which are nuclear design rules, it explicitly take creep effects into consideration. If the plant is subjected to plant startup, steady state, and cool down, due to startup and cool down, it will be subject to fatigue damage, and due to the long-term operation in the creep range, creep damage will be induced. In case of B31.1, since the limits are checked only through the maximum level of stress, as here, and there is no explicit consideration of a creep damage evaluation. This is a conventional Robinson's time fraction rule, which enables the determination of creep life. But in this B31.1, it is not possible. That means evaluation of creep lifetime is not possible. And the whole time here, whole time or operation time at high temperature does not affect the design results. So once design is satisfied according to B31.1, it means that the design is satisfied regardless of the operation time, up to even infinity of time. So it would be necessary to apply the alternative design rules of nuclear design rules, such as RCC MRX. And this is the flow diagram of French RCC MRX code, which is widely used for high temperature piping in nuclear design rules. Depending on the loading type, if it is monotonic, type P procedure should be taken. And if the loading is a cyclic, then type S damage should be taken into account. And by the way, not only in this rule, not only for the stress and fatigue limits, you can see that strain and the creep fatigue limits need to be satisfied. My talk today will be focused on the application in more analytical way. Two approaches. First one is application of, as I said before, alternative rules, nuclear design rules, rather than power piping B31.1, which is the conventional one. Alternative design rules will be has been applied, and the second one is optimization of a piping layout, such as elimination of a redundant pipe support or modification of the piping layout in order to lowering the overall stress level. This is the actual application of a thermal power plant in supercritical Korean thermal power plant. And the piping specs are here given, design conditions, and the operating condition is 575 degrees, and the pressure is 4.4 megapascal, and the number of critical load cycle is 41, and the total hold time or operation time is 81,000 hours. And this is a finite element model, and this is the evaluation results according to ASME B31.1. You can see that, of course, this layout and the loading conditions satisfy the rules of ASME B31.1, and this shows the ratio about 93%. And if we apply the nuclear design rules of RCC MRX, then you can see at the two critical locations, you can see that the design requirements are not satisfied, which means that originally, if this alternative design rules of RCC MRX has been applied to the initial design, then the piping layout and the piping design should have been changed, which may be contributing to the improvement of the integrity. And let me continue my talk with the lowering the stress level, so through elimination of a redundant support. This is the actual setup, actual construction feature of the piping system, and this is a lateral support, which we judged that it is redundant. So we eliminated the redundant support, and we performed the case study to see the effect of the support. This slide shows the evaluation results according to P31 1.1, before and after support removal. And you can see that even after the removal of the support, all requirements are satisfied. And the important thing is here, you can see that the design margins here before removal, design margins here, you can see that margins has been increased a lot. So I would say that integrity has been improved. And in case nuclear design rules were applied before and after support removal, you can see that still the design requirements are not satisfied, which means if fail occurs. And even after removal, fail also occurs. But you can see that the degree of exceeding the limits has been pretty much improved. For example, here, after removal, creep and fatigue damage limit has been within the allowable limits, as you can see. So you can see that after removal of the redundant support, the overall integrity of the piping system can be improved. And the next thing we have done is the modification of a piping layout to optimize and to lowering the stress level, which may be contributing to the enhancing the integrity of the piping system. This is the actual location where two cracks occurred and one crack occurred. This is equal T, and this is a reduced T. This is actual power plant, which has been operating over 9 years. And so we have conducted case studies for the hot rate steam piping, and this is the so-called equalizing line, which makes the two steam equalizing. Equalizing line is, by the way, it is located in the high stress zone, which could be the direct reason to cause the crack. So we have performed, this is the original layout. We performed a loop type piping system to relieve the stress level if possible. The third one is just remove this equalizing line and move this line to another location of a low stress level. And the evaluation results of the three cases, you can see that all results were within the design allowance according to P31 1.1. And by the way, in case of nuclear design rules of RCC-MRX, you can see that case A and the case B, two cases, both design allowance exceeded, fail occurred. But in case of cases C, where the equalizing line moved to the part of low stress level, we found out that most of the important design allowance was satisfied. So we could find out that the integrity of the piping system could be significantly enhanced due to optimization of a piping layout or elimination of redundant support. For all this design evaluation, because the nuclear design rules of RCC-MRX is pretty complicated, we made it in our code, which is called a high temperature design evaluation program. And we used this program, and the high-temp RCC pipe has been used for all this design evaluation. Let me conclude my talk. And integrity of a piping system subject to long-term operation at high temperature in the creep range has been investigated, and the suggestions were made how integrity of the piping systems can be enhanced. The technical issues of P31 1.1 were raised, and as I said before, P31 1.1 is prone to provide non-conservative designs in case of long-term operation in the creep range. To enhance integrity of the piping system subject to long-term service, design evaluations as per nuclear design rules, such as RCC-MRX, needed to be conducted. And through optimization of piping arrangements, including elimination of redundant support or piping layout optimization, integrity of hot rate steam piping can be enhanced. And for those purposes, the web-based high-tech program has been developed by our team, and it can be used for reliable and efficient elevated temperature design evaluations for high temperature component in the piping system. That's it. Thank you.